Hi everyone, this is Dr. Manjunath C. I'm Associate Professor in the Department of Chemistry, RV College of Engineering, Bangalore. In this recording, I'll be discussing about the piezoelectric sensor, which is there in Unit 4, that is Quantum Materials and Smart Sensing, for the course of the Chemistry of Smart Materials and Devices, which has been introduced for the first year uh, Computer Science and Allied branches. Um, So this is the syllabus of Unit 4. In my previous recording, I have covered in detail about electrochemical sensor. In this, I'm exclusively discussing about piezoelectric sensors. Let me go to that piezoelectric sensor slide. So piezoelectric sensors, the piezo is actually the Greek word. It means that the pressure actually, the piezo, the pressure is converted to the electrical energy. So it is a sensor that converts a mechanical stress into electrical signal. It's based on a piezoelectric effect. It is a self-generating sensors do not require any external power. This sensor used for force, or pressure, or vibration, or acceleration, or sound sensing. It's widely used in industrial, automobile, medical, aerospace, and consumer electronics. So this the piezoelectric effect means the generation of electrical charge when a material is mechanically deformed. When a material is mechanically deformed, it occurs in non-centrosymmetric crystal structure. So this is the important requirement for any material to exhibit this piezoelectric effect. Non-centrosymmetric crystal structure. I'll explain what it means later. So actually, there are two types of piezoelectric. Direct piezoelectric, where the mechanical stress directly produces the electrical charge. It's used in sensors. Other one is this phenomena is used in the opposite way, that is called reverse piezoelectric effect. It means that we apply the electric field and make the causes the mechanical deformation. It's exactly reversing the phenomena. That is called actuators. Sensor means the mechanical stress is being converted to electrical energy. Actuators means by applying the electric field, we cause the mechanical deformation. You can see that this picture is representing both the piezoelectric sensor and piezoelectric actuators. In piezoelectric sensor, a force is applied, the mechanical force is applied on this is the piezoelectric material separated by the two metal plates, metal one and metal plates. These are the conductors. Okay, and this is the piezoelectric material. When it is compressed, there is a formation of an electrical energy. Electrical energy is being produced and it is being measured by voltmeter. That is called piezoelectric sensor. But the other way is that by connecting that piezoelectric material to external power source like a battery, okay, by applying the voltage on both the metal plates, we create that mechanical deformation. Either that material may expand or contract, or it may produce some sound. So they are called actuators. Let us look at the mechanism of sensing, the working principle in piezoelectric sensors. So here the mechanical input or the pressure or the force or vibration is applied onto the material. As a result of that, internal dipoles, the dipoles, positive and negative dipoles, gets displaced when you apply the mechanical input. As a result of that, the positive and negative charges they get separated. So as a result of that, the electrical charge appears on the electrode surfaces, the two metal plates. So as a result of that, the voltage is being between the electrical plate is being changed. So that is being measured. The voltage signal is measured, the output, or sometimes the charge is being measured. So whatever that signal magnitude, the intensity of the signal is directly proportional to the applied mechanical stress. So this effect is mathematically represented by in terms of charge Q. Q is actually proportional to the pressure, the applied force. So the proportionality constant is D. So D is actually piezoelectric charge constant. So Q is the charge that is being generated. It is directly proportional to the force applied. So therefore Q is equal to D into F, where D is the piezoelectric constant. Piezoelectric constant is the charge C by N, Newton, C by N. So 1 coulomb of charge D is equal to 1 coulomb of charge being created when 1 Newton of the force is being applied. The output voltage depends on the sensor capacitance. Capacitance means the charge separation, applied stress, and also it depends on the material properties. Let us understand uh, the materials which can exhibit piezoelectric property which are being used. So naturally, the quartz is widely used. Quartz and trackless salt are widely used as a piezoelectric material, and some ceramic materials which are highly sensitive, like PZT. PZT is P means lead, Z means zirconium, T means titanium. So lead zirconate titanate is widely used ceramic based piezoelectric material, and also barium titanate is also used, and lead metaniobate. So these are the ceramic based metal oxide based material. They exhibit piezoelectric property, and polymer materials which are flexible used in various biomedical applications like PVDF, polyvinylidene fluoride, and its copolymer PVDF and TRFE, which are widely used as a piezoelectric material. And currently, as advanced materials like zinc oxide nanowires, aluminum nitrate thin films, and MOS2, it's a two-dimensional material. It's used for 2D piezoelectricity. You can clearly see that this representation, a PVDF, this is actually polyvinylidene difluoride. So you can see the difluoride, and so this is a polymer of vinylidene difluoride. This is the structure of that polymer. You can clearly see that so because of fluorine is highly electronegative. They have delta minus charge, delta minus and delta minus, and this side we will be having delta plus and delta plus charge. Okay, as a result of that, we call it as this is a dipole. So this is a positive and negative poles are oriented in the opposite direction. As when these materials is being sandwiched between the two metal plates, conductors, you'll get a negative charge this side and a positive charge the other side. Okay. So when you apply the load on this, these positive de-align. As a result of that, the charge distribution will change, and because of the charge change in the charge distribution, there will be a change in the voltage, and output also changes. So this is how the piezoelectric material exhibits that property. Let us look at the device structure and its components. It's basically made up of the piezoelectric material, which is very important. This is actually piezoelectric material. Uh, and we have two metal electrodes. This is M1 and M2, two metal plates. It consists of piezoelectric material sandwiched in between the two metal plates. And of course, it is covered with mechanical casings and then electrical output terminals. We will be having electrical output terminals this side and this side. Sometimes include seismic mass for accelerometers and also the protective coating. Okay, and it consists of electrodes and voltage amplifier. If the voltage is very small, to measure small voltage, we need to have voltage amplifier. Charge, if the charge produced is very small, we should have charge amplifier, and signal conditioning unit, and data acquisition system, display controller unit, etc. So these are the components used to construct this piezoelectric device. Let us understand the internal dipole orientation when mechanical load is applied in piezoelectric material. So this is the representation of the charge, non-uniform charge distribution on the metal plate. You can see that you can observe here the negative charge and the positive charge on the metal plates in the three cases, A, B, C. And we have a dipoles of the piezoelectric material. So this is the piezoelectric material sandwiched between two electrodes. And you can see the orientation of the dipoles. Let us discuss one by one in detail. In the first case, okay, in the first case, there is no mechanical load applied here. So again, there is no mechanical load applied on the electrodes. The piezoelectric material is in the unstressed condition in this. You can see that these are the piezoelectric material. They are in unstressed condition. The electric dipoles are aligned along the spontaneous polarization direction. So this is the internal property of that material. This is how the dipoles are aligned in the absence of the stress. So equal and opposite bound charges exist on the top and bottom electrodes. They are equal and opposite charges, negative plus, negative plus, and negative plus. So the polarization remains constant. It's uniform. So this charge is balanced here. This charge is balanced here. So therefore, no potential difference is generated across the external circuit. So therefore, the current is zero. So no current flows through the electrical load. So this state represents the electrical equilibrium. Okay, this is the situation. So in that situation, when you apply the load, okay, when you apply the load, when you compress that material, this is the case B. When you apply the material on that, you can see that when the compression load is applied, mechanical stress is applied along the polarization direction, dipoles become distorted and partially misaligned. You can see that the dipoles distorted and partially misaligned. These dipoles. So net polarization relative to no load condition, that was in the case one, the net polarization decreases relative to no load condition. So the net polarization decreases. You can see that the positive charges decreases here, and here the negative charges decreases this side. As a result, the positive and negative here, the excess charges, excess electrons present here, because the positive charges are less, therefore the electrons are started flowing out. Here there are less negative charges, okay, that more positive charges. So to compensate that positive, the electrons are started flowing here. To balance that surface charge density on the electrodes, the charges started flowing. The charges started flowing. Okay, electrons flows through the external electrical load, and as a result, the current is generated. So this electrical energy is harvested from a mechanical compression. So the compression reduces the polarization and drives charge flow through the load. So this is when the load is applied. Next, in the third case, okay, this is the tensile strength when it is expanded. When the tensile mechanical stress is applied along the polarization, the dipole becomes more perfectly aligned and stretched. Okay, this stretching leads to net polarization increases relative to the no load condition. This increases the net polarization. As a result, you can see that the positive charge increases here and the negative charges increases this side. Okay, but the outside, the charges on the metal are not equal to that. So therefore, to balance that, the surface charge polarity reverses compared to compression. So therefore, it will start moving in the opposite direction. So electrons flows through the load in the opposite direction. So the electrical energy is again harvested from the mechanical tension. Tension increases the polarization and produces the current in the opposite polarity. So this is how the electrical energy is being produced in a piezoelectric material. So mechanical stress changes the polarization in a piezoelectric material, forcing charges to flow through an external load and enabling electrical energy harvesting. So this is the mechanism which is involved in piezoelectric material. So let us look at the ceramic based material, PZT, lead, zirconate, and titanate. This is the piezoelectric material which is widely used, and this is the representation of that sensor. And you can see that this is the metal plate 1 and metal plate 2, and this is the PZT is being sandwiched. Let us look at the structural features. How does that PZT exhibit the piezoelectric material? So this is the commercial PZT possesses the Curie temperature of about 350 degrees centigrade. So it is being made at 350, the poling, okay, the Curie temperature at which it exhibits the piezoelectric behavior. So this is the crystal structure, and the blue color one is the lead. All the corners of the cube are occupied by the lead ion, Pb2 plus, and the red one, which are in the octahedral form, that is on the center of each face of the cube, are occupied by oxide, and the center of the cube are occupied by either titanium or zirconium. Okay, so this is the diagram showing the below Curie temperature. It expands. This is the direction of the polarization, and you can see the change in the position of lead and titanium. It's from centrosymmetric to non-centrosymmetric structure. This is one of the most widely used piezo electric ceramics. It exhibits both ferroelectric and also the piezoelectric properties. It is actually it belongs to Perovskite AbO3 crystal structure. The formula is Pb ZrO3, and you can vary the composition of X by doping zirconium. You can reduce the composition of titanium. Okay, X and 1 minus X. Both zirconium and titanium are +4 oxidation state. This is +4 and this is +2, and they form AbO3 structure. Okay, where the A site is occupied, that is the corners of the cube are occupied by lead, and the B site, the center of the cube, occupied by titanium or zirconium. The oxide ion occupies the corners of the cube. Okay, so this is the structure of PZT. Let us look at uh, the crystal structure. So this structure is non-centrosymmetric. This structure is non-centrosymmetric. So this is very much essential requirement for any material to exhibit piezoelectricity. So why does PZT exhibit piezoelectric property? So because of this non-centrosymmetric crystal structure. What is the meaning of non-centrosymmetric crystal structure? The non-centrosymmetric structure is a crystal structure without a center of symmetry. Without a center of symmetry. It means that a positive and negative charge centers do not coincide. Okay, and if the crystal is inverted, if the crystal is inverted like x2 minus x, y2 minus y, or z2 minus z, the atomic arrangement does not remain the same. Such structures are called non-centrosymmetric structure. So therefore, PZT is having that kind of crystal structure where the positive and negative charge centers do not coincide in this, and creates the permanent electric dipoles. Okay, so therefore, when mechanical stress changes the dipole alignment here, so this results in charge generation. Here, the titanium and zirconium ions are displaced when the pressure is applied from the center of the unit cell. This displacement, you can see here it is in the center and here it is non-center. If you invert this structure, it will not be symmetrical, right? So this displacement of titanium and zirconium ion creates the electric dipoles inside the crystal. Okay, inside the crystal. So PZT contains ferroelectric domains with aligned dipoles. After poling, after poling means when ceramic material is made in the form of pellet and applied at some high temperature, about 350 degrees centigrade, they apply the electrical field to align the dipoles. That is called poling. Domains align in one direction. When the mechanical stress is applied, okay, the dipole alignment changes. When dipole alignment changes, the polarization also changes. So as a result, electrical charge appear on the electrodes. When the stress is removed, charges also disappear. The generated charge is proportional to the applied force. So by that, because of that property, this PZB can be extensively used in various piezoelectric sensors. So there are various types of piezoelectric sensors, like it's been used for the force sensor, pressure sensor, accelerometers, vibration sensors, ultrasonic sensors, and knock sensors. You can find a lot of piezoelectric sensors, commercial sensors available. Those who are interested to work on any EL or PBL project, you can refer this NPJ, Flexible Electronics paper, which is very recently published in 2025. They cover various types of piezoelectric sensors based on polymers and also based on flexible films and composite based for various applications, for sensing and also for actuating and also for energy generating. You can find a lot of ideas from this review article. Um, so these piezoelectric sensors, the advantages are highly sensitive and wide frequency range, and they have a very fast response time, and small size and lightweight. They're compatible, and no external power is required. So limitations are not suitable for static measurements. The output signal is of high impedance. The resistance is high, and there are some temperature sensitivity. If they are polymers, okay, Polymers are organic based, they're sensitive to temperature, and it also requires the proper signal conditioning. And you can find the applications of piezoelectric sensors in various fields, starting from wearable electronics, industries like mechanical vibration monitoring, structural health monitoring, process control, etc. In automobile industries like NOx sensors, airbag sensors, engine condition monitoring, etc. In very importantly, medical ultrasound imaging, heart sound sensors, respiration monitoring, etc. And in consumer electronic like buzzers, microphones, touch sensors, and energy and smart systems like energy harvesting floors, self-powered IoT sensors, wearable electronics. And if you're really interested, you can refer this Chemical Science Royal Society of Chemistry paper, which is a review paper published in 2024. They have exclusively discussed about their applications in wearable electronics, environmental monitoring, and energy harvesting, biomedical applications, and also the structural health monitoring. The next one we have is the strain sensor. Strain sensor is also similar to that piezoelectric sensor. You can see that this is the comparison of strain sensor and physical sensor. And here the output is charge in case of piezoelectric sensor. But in case of strain sensor, the output is the voltage. It is also the similar to that, but yeah, there is a change in the voltage output. And the material that we are using is elastic element. So strain sensor measures the mechanical deformation, the strain. It measures the strain. Strain means the change in the length by original and compared to original length. Okay, either expansion or contraction. It converts the mechanical strain into electrical signal. It is also working on the principle of piezoelectric effect. Stretching leads to increase in the resistance. Compression leads to decrease in the resistance. So that is what it happens in strain sensor. The characteristics are they're highly sensitive. It's like gauge factor. It's also called gauge factor. Good linearity, small size, lightweight, the temperature dependent, and requires signal conditioning. So the materials used for the fabrication of the strain gauge sensors are metals like nichrome, platinum alloys, etc., and silicon, semiconductor material like silicon, germanium, and advanced metallics using carbon nanotubes, graphene for flexible strain sensors. And these strain sensors are widely used in load cells and weighing systems, structural health monitoring, automotive and aerospace testing, pressure and torque measurements, and wearable and biomedical applications. So you can see that these strain gauge sensors are used to measure the strain and stress of the bridges, the highway bridges. Here it is all been fixed. Okay, they keep on monitoring simultaneously the stress of that, and it's widely used in medical industry like the pulse measurement. So pulse piezoelectric sensors are widely sensitive to record the pulse measurement and effective monitoring of patient's health. And also the stethoscopes, due to high sensitivity and robustness of P sensors, they are often used in stethoscopes and anesthesia effectiveness. So these piezoelectric sensors are capable of accurately measuring the muscles stimulations, and hence can be helpful in understanding the effectiveness of anesthesia. And also it is used to for sleep studies. So piezoelectric sensors can be attached to various parts of the patient body and can be used to measure the smallest movements of patients during the sleep also. So these are the two research article. You can download, you can copy and type this link, and you can get the information, and you can read the information. You can use these two articles for your developing the piezoelectric sensor for biomedical applications. Here you can see here it is used to strain based blood pressure sensor, the PPG sensor they have developed. You guys can go through these review article for more details. So with this, I'm summarizing the about piezoelectric and strain sensors in this recording. So piezoelectric sensors convert the mechanical stress and electrical charge, and they work due to change in polarization in non-centrosymmetric materials. So sensor stress is converted to voltage. Actuator is voltage leads to deformation. It's exactly opposite. And we have discussed about the piezoelectric materials like quartz, PZT, PVDF, etc. PZT is made up of lead, zirconium, titanium, and oxygen. It's a perovskite structure, non-centrosymmetric. It is having ferroelectric domains, and the polling leads to the domains are being aligned during the polling, and it is having high piezoelectric coefficients, that is structure property relation. So high piezoelectric means that is C by N. D is equal to C by N. C means the charge divided by N, the force. Even for the small force, there is a large amount of charge is being created. That is called high piezoelectric coefficient. So then piezoelectric sensor structure, it consists of piezoelectric material and two metal electrodes and casings. And they're used, there are various types: force, pressure, vibration, the accelerometers. And these piezoelectric sensors are highly sensitive, fast response, and self-powered. There are some limitations, not suitable for static measurements, and they're temperature sensitive. Applications are they're widely used in industrial vibration and pressure sensing, medical ultrasound and diagnostic, energy harvesting, and automatic sensors. Strain sensors are also called strain gauges. They used to measure the mechanical deformation. It is also based on piezoelectric effect. The resistance changes with the strain. So it is made up of metals, semiconductors, and advanced materials like carbon nanotubes and graphene. It's used in mechanical load and stress analysis, structural health monitoring, and biomedical and wearable prosthetics. So hope you guys have understood about piezoelectric and strain sensors. Thank you.